Hello everyone. I am Dr. Abhijit Shah from Department of Chemistry of SRMIST. I am taking BTech Chemistry course. So this is one chapter from Module 5. I'm making video of this chapter. The name is Composite. Composite. This chapter is very important for BTech engineering students because from this chapter you will understand different type of composite materials. Solid materials is one type. Now, when different solid materials are mixed, it becomes composite. Composite material have many new properties. It can enhance electricity. It can increase the ductile nature of a substance. Okay, so composite material is the main things of this chapter. So in this lecture, I will discuss about different type of composite materials. Okay, so please listen carefully. So another thing is this chapter, it is little bit history type. You have to remember lots of information. Okay. So previously I discussed XPX, XRD, stress strain curve. That is little bit concept based. But here there is also concept, but little bit history type. Means you have to remember things. Okay. There are many names. There are many terminologies you have to remember. Okay. So next, so what is composite material? So composite material is a natural or artificial or synthetic or man-made material system composed of suitably arranged two or more micro or macro or nanomaterials, for example metal, ceramic and polymer, with an interface separating them that differ in form and chemical composition and are essentially insoluble in each other. The design and goal of a composite material. The first goal is to achieve a combination of properties that are not displayed by any of the single material. Right? From that name you can understand that composite means when two materials are involved in one material. So first goal is to achieve a combination of properties that is not displayed by a single material. Second thing, to incorporate the best characteristics or superior properties of each of the component material. And ultimately, third one, to produce a new generation of extraordinary material with improved mechanical characteristics such as stiffness, toughness, and ambient and high temperature strength. Okay, so these are the goal for preparation of a composite material. In nature, there are some composite material. Some naturally occurring materials are also considered to be composite. For example, abalone sheet, wood, bone, and teeth, they are the composite. For example, wood consists of strong and flexible cellulose fiber surrounded and held together by a stiffer material called lignin. Also, bone is a composite of the strong yet soft protein collagen and the hard, right, brittle mineral apatite, whereas abalone sheet is made of calcium carbonate protein. Teeth are made of calcium phosphate and hydroxyapatite. Right? So these are the example of composite material. So from this part, MCQ questions are important. So okay, these names are not to remember for MCQ part. Next one, first one artificial. We discussed natural composite material. Now artificial composite material. An example of an artificial composite is fiberglass, in which small glass fibers are embedded within an epoxy or polyester polymeric material. The glass fiber are relatively strong and stiff but also brittle, whereas the polymer is ductile but also weak and flexible. So when we mix these two materials, the resultant fiberglass is relatively stiff, strong, flexible, and ductile. In addition, it has low density, therefore weight will be less. Another one of the carbon fiber reinforced polymer or CFRP, carbon fiber reinforced polymer composite, carbon fiber that are embedded within a polymer. These materials are stiffer and stronger than glass fiber reinforced material, yet they are more expensive. The CFRP composite are used in some aircraft, aerospace application as well as high-tech sporting equipment like bicycle, golf club, tennis rackets, and snowboards. Okay. Next artificial composite is uh, Piezoelectric steel have a microstructure consisting of alternating layers of alpha ferrite Fe2O3 and uh, Simonite Fe3C. The ferrite phase is a soft and ductile, whereas ceramic is hard and brittle. The combined mechanical characteristics of the Piartile reinforced high ductile and strength are superior to those either of the constituent phases. The important characteristics of composite materials. First one, high strength and stiffness, high modulus, low density, excellent resistance to fatigue, creep, creep rupture, and corrosion. Low coefficient of thermal expansion. They provide product design flexibility and high strength to weight ratio. Next, application and uses of composite. First one, in automobile industries. Automobile parts like component of engine, spray nozzles, uh, mudguards, tires, etc. Second is aeronautical application. Structural component like wings, body, stabilizer, and fuel of aircraft, rocket, army missile in military, etc. Third application in marine application, that shaft, hulls, spars, and other part of ship. Safety equipment like helmet, we are using composite material. Different sports equipment like tennis racket, golf stick used composite material. In communication industry like preparation of antenna and electronic circuit board, we are using composite material. Next thing is what is matrix and dispersed phases. Many composite material are composed of just two phases. One is called matrix, which is continuous and surround other phases, often called dispersed phases. The properties of composite are function of the properties of the constituent phases, their relative amount, and the geometry of the dispersed phases. Dispersed phase geometry in this context means the shape of the particle and particle size, distribution, and orientation. These characteristics are presented here. Okay, so matrix, this is called matrix, blue one. In matrix, whatever the material is present, that is called dispersed phase. Matrix phase, the primary phase, having continuous character, is called matrix. matrix is usually more ductile and less hard phase. It holds the dispersed phase and share a load with it. Now next one, disperse, reinforce phase. So the second phase or phases which is embedded in the matrix in a discontinuous form, that is called dispersed phases. This second phase is called the dispersed phase. The dispersed phase is usually stronger than the matrix. Therefore, it is sometimes called reinforcing phase. Reinforcing phase. Next, classification of composite material based on reinforcing material structure. So in composite material, there is a dispersed phase, which is the reinforcing material. So based on reinforcing material, we can classify the composite material. First one, particle reinforced, fiber reinforced, and structural. Particle reinforced, two type, larger particle, dispersion. Okay, another one, dispersion strengthened. Fiber reinforced, continuous and discontinuous. Structural, laminates and sandwich. Now discontinuous here aligned and randomly oriented. Okay, so these are the classification of composite material based on the reinforcing material. The main type of reinforcement used in composite material are aligned, continuous fiber, discontinuous fiber, elongated single crystal, particles, numerous forms of fibrous architecture produced by textile technology such as fabrics and carbon nanotube are similar to discontinuous fiber. In composites, solid materials are classified into 4 classes: polymer, metals, ceramic, and carbon. There are reinforcement and matrix material in each category. First one, particle reinforced composite. It is a type of composite material in which discontinuous phase, that is dispersed phase, is a particle. It is two types: larger particle composite and dispersion strengthened composite. Now we have to describe what is larger and what is dispersion strengthened composite. In case of larger particle composite, the particle matrix interaction cannot be treated on the atomic or molecular level. Okay. Rather, continuous mechanics is used. Most of these composites, the particular phase is harder and stiffer than the matrix. This reinforcing particle tends to guard the movement of the matrix phase in the vicinity of each particle. In reality, the matrix transfers some of the applied stress to the particle, which bear a fraction of the load. The degree of reinforcement or improvement of mechanical behavior depends on the strong bonding at the matrix particle interface. And dispersion strengthened composite. It is the particles are normally much smaller and diameter will be between 0.1 to 1 nanometer or 10 to 100 nanometer. Okay. Next one, this is called, these are the examples. One is larger particle composite A and dispersion strengthened composite. Okay, so when particle size is larger, when particle size is small, that's called dispersion. Next, example of larger particle composite. That is metal, in metal, that is cobalt or nickel matrix phase, and ceramic base, that is dispersion phase. Larger particle composites are utilized with all three material type: metal, polymer, and ceramic. The ceramic are the ceramics are the example of ceramic metal composite. Ceramate. The most common ceramate is the ceramated carbide, which is composed of extremely hard particle of a refractory carbide ceramic such as tungsten carbide or titanium carbide embedded in a matrix of a metal such as cobalt or nickel. The composites are utilized extensively as cutting tools for hardened steel. The hard carbide particle provided the cutting space, but being extremely brittle are not themselves capable of withstanding the cutting stress. Toughness is enhanced by their inclusion in the ductile metal matrix, which isolates the carbide particle from one another and prevent particle-to-particle crack propagation. Both material and particulate phases are quite refractory to withstand the high temperature generated by the cutting action of the material that are extremely hard. No single material could possibly provide the combination of the properties possessed by ceramite. So ceramite is a very good composite. Okay. Next one, concrete. Concrete is a common large particle composite in which both matrix and dispersed phase are ceramic material. Since the term concrete and ceramics and cement are sometimes incorrectly interchanged, perhaps it is appropriate to distinguish between them. In broad sense, concrete implies a composite material consisting of an aggregated particle, dispersed phase, that are bonded together in a solid body by some type of binding material, that is cement, matrix phase. The two most familiar concrete are those made with the Portland and apathetic cement, where the aggregate is a gravel and sand dispersed phase. Apathetic concrete is widely used primarily as a paving material, where Portland cement concrete is employed extensively as structural binding material. Asphalt, that is called matrix, is sticky black, highly viscous liquid or semi-solid form of petroleum. Okay, next one, reinforced concrete. The strength of a Portland cement concrete may be increased by addition of reinforcement. This is gradually accomplished by means of steel rod, wire, bar, or mesh, which are embedded into the fresh and uncutted concrete. Thus, the reinforcement renders the hardening structure capable of supporting greater tensile, compressive, and shear stress. Even crack developed in the concrete, considerable reinforcement is maintained. Steel serves as a suitable reinforcement material because its coefficient of thermal expansion is nearly same as that of concrete. In addition, steel is not rapidly corroded in cement environment, and relatively strong adhesive bond is formed between it and the cured concrete. This adhesion may be enhanced by incorporation of contour into surface of the steel member, which permit a greater degree of mechanical interlocking. Next, carbon black reinforcement rubber. Both elastomer and plastics are frequently reinforced with various particulate material. Reinforcing particle material such as carbon black is used in modern rubber. Carbon black consists of very small and essentially spherical particles of carbon, produced by the combustion of natural gas or oil in an atmosphere that has only limited air supply. This extremely expensive material enhances tensile strength, toughness, and resistance when added to vulcanized rubber. Automobile tires contains on an order of 15 to 30% volume of carbon black. For the carbon black to provide significant reinforcement, the particle size must be extremely small, within diameter 10 to 50 nanometer. The particles must be evenly distributed throughout the rubber and must form a strong adhesive bond with rubber matrix. Particle reinforcement using other material like silica is much less effective because this special interaction between rubber molecule and particle surface does not exist. Dispersion strengthen composite. Metal and metal alloy may be strengthened and hardened by the uniform dispersion of several volume percent of fine particle of every hard and inert material. The dispersed phase may be metallic or non-metallic. Oxide material are often used. Again, the strengthening mechanism involves interaction between the particle and dislocation within the matrix as with participating hardening. The dispersion strengthening effect is not pronounced as participating hardening. However, the strengthening is retained as elevated temperature and for extended period because the dispersed particles are chosen to be unreactive with matrix phase. The high temperature strength of nickel alloy may be enhanced significantly by addition of about 3% volume of TiO2 as finely dispersed particle. This material is known as thoria dispersed or TD nickel. The same effect is produced in the aluminum oxide system. A very thin and adherent aluminum coating is caused to form on the surface of extremely small 0.1 to 0.2 micrometer thickness flakes of alumina dispersed phase, which are dispersed within an aluminum metal matrix phase. This material is termed sintered aluminum powder. Fiber reinforced composite. A type of composite material in which the discontinuous phase, that is dispersed phase, is fiber. It is two types. One is continuous and another one discontinuous. The key fiber for mechanical engineering application are glasses, carbons, also graphite, and several types of ceramics and high modulus organic. Three main synthetic fibers used to reinforce particles are glass, aramid, and carbon. Most of the key fibrous reinforcement are made of brittle glass, ceramic, or carbon. The mechanical characteristic of a fiber reinforced composite depends not only on the properties of the fiber but also on the degree to which an applied load is transmitted to the fiber by matrix phase. A critical fiber length is necessary for effective strengthening and stiffening of the composite material. The critical length is on order of 1 nanometer, which range between 20 to 150 times the fiber diameter. There is some calculation, this is not so much required. Next one, fiber used in fiber reinforced plastic or polymer. Example: glass fiber, carbon or graphite fiber, and aramid fiber. Glass fiber are used primarily in reinforcement polymer. Characteristics: high strain to weight ratio, good mechanical stability, good resistance to heat, cold moisture, uh, cold moisture and corrosion resistant. Okay, good electrical insulation properties. These are the characteristics. The glass fiber reinforced polymer. E-glass fiber are the first important structural composite reinforced for continuous fiber, originally developed for electrical insulation application. E-glass uh, is by many of order of magnitude the most widely used for all reinforcement. The primary reason for this are their low cost and early development composite to other fiber. Glass fiber are produced as multi-filament bundle, filament diameter ranging 3 to 20 micrometer. H-glass or Hs are stiffer and stronger than E-glass and have better resistance compared to E-glass. Next one, carbon fiber reinforced polymer. Carbon or graphite fiber, often called graphite fiber in United States, are used reinforcement for polymer, metal, ceramic, and carbon. Aramid fiber polymer reinforced polymer. Aramid is an aromatic amide fiber, is the high modulus organic reinforcement, primarily used to reinforce polymer and cement and for ballistic protection. Fiber based on alumina. Alumina based fiber are primarily used to reinforce metal and ceramics. High density polyethylene fiber. High density polyethylene fiber are primarily used to reinforce polymer for ballistic protection. Fiber based on silicon carbide. Silicon carbide based fiber are primarily used to reinforce metal and ceramic. These are a number of commercial fiber based on silicon carbide. Next is structural composite. A structural composite is normally composed of homogeneous and composite material, the properties of which depends not only on the properties of constant material but also on the geometrical design of the various structural elements. Laminar composite and sandwich panel are two of the most common structural composites. What is laminar composite? A laminar composite is composed of two-dimensional sheet or panel with a preferred high-strength direction such as wood and continuous aligned fiber reinforced plastic. The layers are stacked and subsequently cemented together such that orientation of the high strength direction varies with each successive layer. For example, adjacent wood sheet in plywood. Next one, sandwich panel, is considered a class of structural composite are designed to be lightweight beams or panels with relatively high stiffness and strength. A sandwich panel consists of two outer sheets or faces that are separated by an adhesively bonded to a thicker core. The outer sheets are made of a relatively stiff and strong material, typically aluminum alloy, fiber reinforced plastic, titanium steel. The impact they impact high stiffness and strength to the structure and must thick enough to withstand tensile and composite stress that are result from loading. The core material is lightweight and typically has low modulus of elasticity. Classification of composite mineral based on matrix material. One is metal matrix composite, ceramic matrix composite, polymer matrix composite, and carbon matrix composite. Next is important is metal matrix composite. Metal matrix composite is the matrix. The matrix is ductile metal. This material may be utilized at high service temperature than their base metal is a metal counterpart. Furthermore, the reinforcement may improve specific stiffness, specific strength, resistance, thermal conductivity. Okay, so these are the advantages of metal matrix composite. Next one, ceramic matrix composite. Ceramic is the art and science of making objects from inorganic, non-metallic material by action of heat. The key ceramic used as in CMC, ceramic matrix, silicon carbide, alumina, silicon nitride, etc. Last one, polymer matrix composite. Polymer matrix composite used in FRP, fiber reinforced plastic and polymer. It consists of polymer resin as matrix with fiber as the reinforcement medium. These materials are used in greatest diversity of composite application. Aramid fiber reinforced composite. So aramid fiber are high tensile strength, high modulus material that were introduced in the year early 1970. They have outstanding strength to weight ratio, which are superior to metal. Chemically, this group of material is known as polyparathylene terephthaldehyde. There are a number of aramide materials. Okay. Trade names for two of the most called Kevlar and Normex. Okay, so these are the aramid fiber reinforced polymer composite. Last one, polymer matrix material. So the role of the matrix often to determine the maximum service temperature, since it normally soften, melt or degrade at much lower temperature than the fiber reinforcement. Okay, so these are the things. You have to know what is the example. For example, PEEK. So a bit difficult little bit name. Poly ketone, polyethylene ketone. Right? So it's difficult name little bit, but not required so much. But you have to know what is polymatrix material. Okay, so these are the things for metal matrix composite. There is very little thing to understand, but more important is to you have to remember many things. Okay, so that's all about this lecture. Okay, fine. Thank you for listening.